In this video, we will do an example that involves checking if we can use the intermediate value theorem on it or not. So this is from worksheet 4, problem number 6, parts A and B. So just A and B of this example. So I want to begin by having you pause the video for 5 minutes to read and try this problem. 4, 3, 2, 1, pause the video, pause it and try this for 5 minutes. All right, so hopefully you did that. Hopefully you paused it and tried it for about 5 minutes. Let's talk about it together. For part A, it wants us to calculate f of 0 and f of 2. So if I plug 0 into this, we get e to the 0 minus 0 squared over 0 minus 1. And e to the 0 is 1, so 1 minus 0 on the top is 1. Denominator is negative 1, and that simplifies to negative 1. So that is f of 0. For f of 2, plugging that in, we get e squared minus 2 squared over 2 minus 1. So the denominator is just 1, so we get e squared minus 4 over 1, which just becomes e squared minus 4. Alrighty, so that is f of 2. Part B now asks, can the intermediate value theorem be used with just part A, just what we did in part A, to show there's an x-intercept of this function? So an x-intercept would be like if I have my graph and I have something like this point where it crosses that x-axis. Trying to see if there's a point where that y value is 0. Okay, so if I can, then determine a range of values within which the root exists. So that's talking about some interval within which I know that that root is going to exist. But if not, where does the intermediate value theorem break down? So the key observation with these two numbers is that negative 1 is less than 0. That is negative. And f of 2, because e is greater than 2, e is about 2.7, when I square this, e squared is going to be greater than 2 squared. It's going to be bigger than 4. So because of that, e squared minus 4 is a positive number. So it certainly seems like on the interval from 0 to 2, because one of these endpoints has a negative output and the other endpoint has a positive output, somewhere in the middle it seems like the y value should be 0. But there's a problem. There's a problem with this function somewhere in the interval from 0 to 2. And the problem is at x equals 1, that denominator is 0. This function is discontinuous at x equals 1. So we are ready to write our answer now for B. Because of that, we can't use the intermediate value theorem, IVT, on this interval from 0 to 2, since my function f is not continuous on that whole interval. That's not continuous on the whole interval from 0 to 2, because as we saw, f is discontinuous at x equals 1, because plugging that in, it makes my function undefined. So the intermediate value theorem for this function, it breaks down on the interval from 0 to 2, because our function is just not continuous on that whole closed interval. In part C, I'm not going to talk about it in this video, but it would be a good follow-up question. It asks us to show that f, this function, actually does have at least one x-intercept. So maybe there's going to be a way to apply the intermediate value theorem somewhere else where it won't break down. And that's what part C is all about.